Imagine waking up one morning and discovering that time itself has stopped. Clocks show the same minute forever. Coffee cups sit mid-sip, smoke from a candle hangs frozen in the air, and sunlight is caught in one steady beam. It's a dramatic image, and it gets to the heart of some of the deepest questions physics asks. What does it mean for things to change? Why does change seem to have a direction, yesterday to today, cold to warm, lived to dead, and could that direction ever come to an end? To answer that, we need to get friendly with a concept called entropy. Entropy is a measure of how many microscopic ways a system can be arranged while looking the same at a larger scale. That definition sounds technical, but you can get the idea from a few household examples. Take a tidy bedroom. There's one way for the bed to be neatly made and toys in their places. There are countless ways for the same bed to be messy. Pillows askew, clothes scattered, books on the floor in different arrangements. The messy room corresponds to many more microscopic arrangements than the tidy room. Entropy, in this picture, is essentially counting those microscopic arrangements. The more ways to make something look the same overall, the higher its entropy. Another classic example, mix cream into coffee. Before you stir, the cream and coffee are mostly separate. After stirring, they're blended into a smooth, brown swirl. The mixed cup can be achieved in an extraordinary number of microscopic ways, billions upon billions of molecular positions that look the same overall. The unmixed state is one special arrangement among far fewer microscopic possibilities. That's why you never see cream spontaneously unmix and leap out of the cup to form perfect layers again. It's not that the laws of physics ban it outright, it's that such an event is so astronomically unlikely. Entropy is about probability. There's a compact formula that physicists often use, S equals K ln omega. S is entropy, K is Boltzmann's constant, a tiny conversion factor that makes the units work, and omega, the Greek letter omega, is the number of microscopic arrangements, sometimes called microstates. The logarithm is there because these numbers get unimaginably large. The logarithm turns them into manageable sizes. The physical takeaway is simple. More microstates means more entropy. Entropy is central to thermodynamics, the branch of physics that studies heat, work, and energy. Thermodynamics has a few core laws that are remarkably robust, and they're worth meeting in plain language. Zeroth law. If object A is in thermal balance with B, and B is in thermal balance with C, then O is in thermal balance with C in everyday terms. This is just the idea of temperature as a measurable quantity. If two things stop exchanging heat, their temperatures are equal, and that allows us to use thermometers sensibly. First law, energy is conserved. You can't create or destroy energy, you can only convert it from one form to another. Heat engines, refrigerators, and every chemical reaction obey this. When you burn fuel, you're converting chemical energy into heat, light, and motion. Second law, in a closed system, entropy tends to increase. Put more simply, processes that involve energy spreading out are overwhelmingly likely. Processes that concentrate energy spontaneously are overwhelmingly unlikely. Heat flows from hot to cold, not the other way around. Your cream mixes into coffee and doesn't unmix. This law gives us the direction of time, what we call the arrow of time. Third law, as a system approaches absolute zero temperature, its entropy approaches a constant minimum, often zero for a perfect crystal. Practically speaking, you can get colder and colder, but reaching absolute zero exactly is impossible with finite operations. The second law is the one people often latch onto when talking about time stopping or the universe ending. If entropy keeps increasing, will it one day max out? If entropy hits a maximum, what happens to change and to our experience of time? Before pushing too far, it's important to say what entropy is not. Entropy is not disorder in the loose everyday sense, at least not wholly. Disorder is a helpful metaphor in simple cases, but entropy is really about the number of microstates compatible with a macrostate. Sometimes gravitationally clumpy things, like a star or black hole, have enormous entropy, even though they look ordered by eye. So think of entropy as how many ways things can be arranged without changing what you see at large scale, or as how much information is missing about the exact microscopic details. Why does the universe have an arrow of time at all? The microscopic laws of physics, Newton's laws, Maxwell's equations, the Schrödinger equation in quantum mechanics, are time-symmetric. If you watched a movie of individual atoms moving and then played it backwards, the motion obeys the same fundamental equations. Yet at our scale, eggs scramble but don't unscramble. The resolution lies in statistics and boundary conditions. The equations allow both directions, but the probability of ending up in a low-entropy state from a high-entropy one is vanishingly small. The universe started in a very special, very low-entropy state at the Big Bang. That initial condition is the reason we have an arrow of time. Entropy has been increasing ever since, making the forward direction the future. Why the early universe was so low in entropy is an open question, and one of the deepest puzzles in cosmology. Inflation, a period of rapid expansion in the very early universe, helps explain the uniformity and flatness of the cosmos, but whether and how it explains the low initial entropy is still debated. Let's take this statistical idea and scale it up to cosmic proportions. Think of the universe as a giant thermodynamic system. For much of cosmic history, it wasn't in equilibrium. There were temperature gradients, clumps of matter, and lots of available free energy to do work. Stars shine because gravitational collapse freed energy and turned it into nuclear reactions. That energy supports living systems that take advantage of gradients. Life, machines, and any process that does something relies on usable energy differences, on free energy. Free energy is the part of the total energy you can use to perform work. As entropy increases, free energy tends to decrease. Energy spreads out and becomes less available for doing useful things. When a system reaches thermodynamic equilibrium, maximum entropy for the constraints in place, free energy is gone, and macroscopic changes stop. At that moment, nothing useful can be done. No engines run, no stars shine, no life survives. That's the essence of the heat-death idea. Heat death, or the Big Freeze, is the picture where the universe ends up in thermal equilibrium with maximum entropy. Temperatures become uniform, no gradients exist, and nothing can perform work. It's important to distinguish heat death from the notion of absolute emptiness. A heat-dead universe can be filled with a faint uniform sea of low-energy photons and other particles. It's not zero energy, it's just that the energy is spread so evenly it's useless. How might the universe get there? Several processes push things in that direction over staggeringly long timescales. Stars burn through their nuclear fuel over billions to trillions of years. The longest-burning stars, the tiny red dwarfs, can simmer for up to about 10 trillion years before they grow dim and die. Once star formation winds down, galaxies become populated by white dwarfs, neutron stars, and black holes. Over much longer times, these remnants cool. White dwarfs slowly radiate away their heat and fade. Black holes, paradoxically, contain a lot of entropy, more on that in a second, and they themselves don't last forever either. Black holes are central to modern thinking about cosmic entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to the area of their event horizons. The formula is SBH equals Kc3 / 4gh where A is the area of the horizon. The important upshot is that black hole entropy is enormous compared to ordinary matter. A supermassive black hole sitting at the center of a galaxy can contain more entropy than all the ordinary matter in that galaxy combined. When we total up the entropy in the observable universe, black holes dominate the count. Stephen Hawking also showed that black holes aren't entirely black. Quantum effects near the horizon let them slowly emit radiation, Hawking radiation, and lose mass. Over stupendously long timescales, black holes evaporate. The lifetime of a black hole scales roughly with the cube of its mass, so very massive ones live unimaginably long lifetimes, far beyond the current age of the universe. For a stellar mass black hole, the evaporation time is on the order of 1067 years. For a supermassive black hole of a billion solar masses, lifetimes reach something like 1090 to 10100 years. When those black holes evaporate, they release their energy back into the cosmos in a dilute bath of low-energy radiation, increasing the overall entropy even further. Cosmologists like to sketch a timeline of the long-term future in broad eras. While details vary by source, a commonly cited sequence goes roughly like this. The stelliferous era, now to roughly 1014 years. Galaxies, stars, and planets dominate. Star formation continues, though it will decline, and complex chemistry and life are possible. The degenerate era, 1014 to about 1037 years, star formation ceases. The universe is populated by stellar remnants, white dwarfs, neutron stars, and black holes. Slow processes like collisions and ejections change things over long timescales. The black hole era, 1037 to around 10100 years. Black holes are the main players. They slowly accrete matter where available and then evaporate via Hawking radiation over stupendously long spans. The dark era beyond 10100 years. After black holes evaporate, the universe is mostly low-energy photons, electrons, positrons, and perhaps some stable exotic particles. The energy is spread thinly. There are no significant free energy gradients left to do work. Entropy is close to maximum for the current conditions. These numbers are jaw-dropping, and one reason the story feels abstract is that it plays out on timescales so long human intuition struggles to hold them. But the physics behind the timeline rests on well-tested principles and reasonable extrapolations. Nuclear burning timescales, gravitational dynamics, quantum mechanics of black holes, and the expansion history of the universe. The universe's expansion plays a crucial role. Observations over the past 2 decades show that the expansion is accelerating, driven by what we call dark energy. The simplest model for dark energy is the cosmological constant, a constant energy density filling space. In a universe dominated by a cosmological constant, the expansion accelerates forever and distant galaxies recede beyond our horizon. Locally bound systems, like galaxies and clusters, remain intact for a long time, but eventually the observable part of the universe becomes sparser and colder, as the cosmic microwave background redshifts to longer and lower energy photons. An intriguing and subtle twist comes from the thermodynamics of spacetime itself. A universe dominated by a positive cosmological constant approaches a de Sitter state in the far future. De Sitter space has a temperature and an associated entropy related to the area of its cosmological horizon, the boundary beyond which events can never affect an observer. This entropy is finite and proportional to the horizon area, not to volume. The existence of a cosmic horizon with entropy and temperature makes large-scale thermodynamic questions more subtle. In this picture, the maximum entropy state might be de Sitter space, and once the universe approaches that, the evolution of local degrees of freedom effectively halts in the sense that no new macroscopic work can be extracted. So does time stop in such a universe? Not in the literal sense that clocks freeze their hands, but operationally many of the things we think of as time could vanish. Time as we measure it is based on change, oscillations of atoms, motion of hands, cycles of processes. If everything is in thermal equilibrium, there are no persistent macroscopic processes to serve as clocks. Quantum fluctuations still happen, but without usable gradients, those fluctuations are random and cannot be harnessed into ordered processes. From the standpoint of an observer who relies on change, the universe has become unchanging. That phrasing, from the standpoint of an observer, matters, because physics distinguishes between fundamental time and experienced time. Fundamental time is a coordinate in the laws of physics, a parameter in equations like Schrödinger's or Einstein's. Experienced time is the sequence of changes that observers can detect. A universe could continue to have a parameter we call time without undergoing macroscopic change. So whether time stops becomes a question about the physical relevance of the time parameter when no processes exist to mark it. There are speculative scenarios where something more dramatic happens than heat death, situations in which time, in a deeper sense, might end. One such possibility is the Big Rip. If the dark energy density increases over time, a form of energy with equation of state W-1, often called phantom energy, the expansion rate accelerates so violently that eventually all structures are torn apart, from galaxy clusters down to atoms, at a finite time in the future. At the Rip singularity, physical quantities can blow up, and the classical description of spacetime breaks down. In such a scenario, you could say the familiar laws governing the flow of events break down at a finite time. But whether time ends as a meaningful concept depends on unknown quantum gravity effects that would take over at extreme conditions. Another dramatic possibility is a vacuum decay. Our current universe might be sitting in a false vacuum, a metastable state that could quantum tunnel to a lower energy, true vacuum. If this happened, a bubble of true vacuum would form and expand at nearly the speed of light, converting the region it sweeps through into the new vacuum. The laws of physics inside could be different. Particle masses, forces, and even dimensionality might change. For anyone inside the bubble's wall, the change would be catastrophic and could be said to end the previous way of keeping track of time. But time itself would continue inside the new vacuum. It's just that the rules governing processes, and hence clocks, would be different. Vacuum decay is speculative but not conjured out of nothing. Particle physics models allow such tunneling, and calculating its likelihood is an active area of research. Current best estimates, given what we know about the Higgs boson and other parameters, suggest we're safe for vastly long times, but the numbers depend on unknown high-energy physics. There's also a subtle line of thought that links the arrow of time to boundary conditions. If entropy reaches a global maximum and stays there forever, the concept of an arrow of time disappears because there's no longer any meaningful asymmetry between past and future. But that disappearance is about our ability to tell past from future, not about time as a mathematical parameter. Some physicists explore the idea that the arrow of time might be a consequence of cosmological boundary conditions, and that different boundary choices could produce different apparent directions of time in different regions. These ideas are speculative and philosophical in flavor, but they show how intertwined entropy, cosmology, and time are. One apparent paradox that pops up in heat-death discussions is the Boltzmann brane problem. Given enough time in a state of thermal equilibrium, random fluctuations could spontaneously produce complex arrangements purely by chance, including a single brain with false memories of a past. If the universe lasts for an extremely long time in a state where such fluctuations are possible, it seems more likely, by naive counting, that observers would be isolated Boltzmann brains than that full, structured universes like ours would exist. That contradiction, our clear evidence of a consistent, structured past, suggests some subtlety in how we count observers or how we apply probabilities in cosmology. Different measures and assumptions change the outcome, and many researchers consider Boltzmann branes a problem for certain cosmological models rather than a literal expectation. It's another sign that the end states of the universe raise deep conceptual puzzles besides the raw thermodynamics. Let's return to gravity, because it behaves a bit differently than textbook thermodynamics of gases. Gravity tends to make matter clump, and clumping can create low-entropy configurations locally, like stars and planets. How can that square with entropy increasing? The key is that when matter collapses gravitationally, it releases energy, often as radiation, which increases the entropy of the surroundings by an amount greater than the decrease associated with the more ordered-looking mass configuration. For instance, when a gas cloud collapses to form a star, the cloud sheds energy as photons. Those photons spread out and their entropy increases hugely. Overall, total entropy rises, even though the collapsing matter looks more ordered. In the end, gravity enables stars to form and burn, creating huge entropy increases across the cosmos. Thinking about entropy on cosmic scales led some physicists to propose radical ideas about the origin of the universe's low entropy. One approach imagines our observable universe as part of a larger multiverse in which different regions have different physical conditions. In that setting, most regions might be high entropy or inhospitable to complex structures, while a small subset of regions have low entropy and support complex processes. Our existence in such a region would then be a selection effect. We observe low entropy because only in such regions can observers arise. This line of thought overlaps with anthropic reasoning and is controversial. It can explain some things, but often pushes questions to the structure and measure of the multiverse. Another angle is to think about information. Entropy is closely linked to missing information about microstates. If you have a complete microscopic description, the entropy is low. If you have little information, entropy is higher. Some speculative theories treat spacetime and gravity as emergent from underlying quantum information processes. In those pictures, time and geometry might arise from entanglement patterns, and the arrow of time could be tied to how entanglement spreads. These ideas are cutting-edge and not settled, but they show that questions about entropy and time touch the foundations of physics. There's also an operational way to think about time stopping. Our clocks are physical systems that undergo regular, repeatable processes, oscillations in cesium atoms, vibrations of quartz crystals, ticks of a mechanical escapement. To the extent that these processes rely on gradients and non-equilibrium conditions, they require free energy. In the heat-death scenario, free energy disappears, and clocks would cease to tick in the usual sense. That's the practical meaning of time stopping for creatures or machines. Without change, no measurement of duration is possible. But even in a high-entropy universe, irreducible quantum processes can continue. Quantum fields in de Sitter space, for example, are associated with a finite temperature, the Gibbons-Hawking temperature, and that means fluctuations persist. Whether those fluctuations can be used to define a persistent arrow of time or to generate ordered complexity is doubtful, but they mean that nothing happens, in the strictest sense, is not automatic. Instead, what happens is random, unstructured noise, not the sequence of organized events that forms histories rich in cause and effect. If we look at more exotic speculative theories, there are other ways time might end. Some approaches to quantum gravity suggest that spacetime is discrete at the smallest scales and that the continuum picture breaks down at the Planck scale. If time is emergent from a network of quantum relations, then very different behavior could occur in extreme regimes. These ideas are currently mathematical and conceptual work in progress. They suggest that what we mean by time, at human scales, might not even be a fundamental ingredient at Planckian scales. But connecting those ideas to a cosmological heat-death scenario is a big leap and requires more empirical and theoretical development. One takeaway here is that the question, could the universe freeze forever, is both simpler and more subtle than it seems. The simple part: yes, many standard models in cosmology predict a future where usable energy runs out and macroscopic processes cease, a practical freeze-out where nothing interesting happens and the experienced arrow of time disappears. The subtle part: there are many ways the cosmos could avoid that fate, and many technical subtleties in what freeze and time stopping actually mean. Dark energy might change behavior, the vacuum might decay, black holes might dominate entropy accounting differently than we expect, or fundamental physics could reveal new mechanisms. Another practical piece of the puzzle is the role of conservation laws and symmetries. Energy conservation is local in general relativity, and defining total conserved energy for the whole universe is tricky because of the expansion of space. This technical landscape makes talking about the total energy and its availability a careful exercise. However, the qualitative behavior, the draining of free energy into unusable forms as entropy increases, holds across many frameworks. Thinking about all this raises a human question: why should we care? The timescales involved are far beyond any human planning horizon, so why dwell on eventual heat death? Partly it's the intellectual drive to understand the fate of the cosmos, the same curiosity that asks how life began, what the sun will do, and whether there are other universes. Partly it's philosophical. The thermodynamic arrow of time ties into our experience of causation and memory. If the arrow of time is ultimately a statistical consequence of an early low-entropy state, then explaining that initial condition may reveal new laws or principles about the universe. And partly it's practical for physics. Thinking about entropy, horizons, and the interplay of gravity and thermodynamics has led to deep insights in quantum gravity, black hole physics, and the information paradox. If you want a concrete way to picture what a heat-dead universe looks like to a hypothetical observer, imagine being in a room with no gradients. Uniform temperature, no light source, no changing fields you can use to power any process. In that setting, you could no longer build a clock, harness energy, or sustain a metabolism. To an internal observer, time as experienced, the sequence of meaningful events, ends. But as a mathematical variable in physical laws, time still exists. It's just irrelevant to living things. All of this sets the stage for some deeper investigations. One next point to explore is how different theories of dark energy change the long-term thermodynamic picture. Another is how quantum mechanics at cosmological scales, like the behavior of de Sitter horizons and the statistical mechanics of spacetime, might revise our estimates of future entropy. We can also dig into the thorny problem of why the early universe had low entropy in the first place, and what that tells us about initial conditions, inflation, and possible multiverse scenarios. Each of these directions opens up a mix of settled science, active research, and genuine mystery, and they help turn the dramatic image of time stopping into a nuanced, fascinating scientific story. If the story so far has a theme, it's this. The large-scale future of the universe is shaped by a few big players: entropy, gravity, and the mysterious dark energy that's driving cosmic acceleration. We've seen one clear endgame: heat death, where usable energy runs out and nothing interesting happens anymore. But the physics lets lots of different endings, detours, and technical wrinkles into the plot. Let's unpack some of the next important twists, starting with dark energy itself, because how it behaves changes everything. Dark energy is our name for the thing that makes space expand faster as time goes on. We don't know what it really is. We have observations that measure its effect, and the simplest model that matches those observations is a number called the cosmological constant, a fixed energy density that fills space uniformly. If the cosmological constant really is constant, then the long-term picture is fairly tidy. The universe continues to accelerate, distant galaxies slip beyond our horizon, and the observable patch approaches a de Sitter state, a spacetime with a constant vacuum energy. That de Sitter state comes with a temperature and an entropy associated not with matter but with the horizon itself, and that has powerful thermodynamic consequences. But dark energy could be something else. It might be a field slowly changing over time, sometimes called quintessence. It might even be something exotic that grows stronger as the universe expands, nicknamed phantom energy, which would produce a big rip that tears apart structures at a finite time. Or dark energy might be a temporary phenomenon and later give way to a completely different cosmic behavior. Each possibility alters the destiny of entropy, horizons, and the availability of free energy, and therefore the fate of any beings or computers that try to hang on. If dark energy stays constant, the de Sitter scenario brings in a striking idea. The universe has a finite maximum entropy. For everything inside a de Sitter horizon, the total number of available microstates that describe the entire observable patch is finite and proportional to the area of the horizon. That finiteness is surprising because we usually imagine space as containing arbitrarily many degrees of freedom, but horizons change the bookkeeping. The practical upshot is that a system with finite entropy evolving for an exceedingly long time has some counterintuitive behaviors. One is recurrence. Given enough time, the system will eventually return arbitrarily close to earlier states. This is a version of the Poincaré recurrence theorem applied in a statistical sense. Given a finite state space and reversible dynamics, trajectories eventually revisit neighborhoods of past states. Those recurrences happen on timescales that blow past imagination, often doubly or triply exponential in entropy, but their existence forces philosophers and physicists to ask, if the universe lasts forever and has finite entropy, then random fluctuations over inconceivably long times will produce almost any configuration allowed by the rules, including isolated brains with false memories and perceptions, so-called Boltzmann brains. If Boltzmann brains vastly outnumber ordinary observers like us across the ensemble of times and fluctuations, then our own existence as reliably embedded observers in a long history of a structured cosmos becomes unlikely. This is the Boltzmann brain problem in a nutshell. Naive application of statistical reasoning in a large, long-lived system can lead to the absurd prediction that most observers are random, fleeting fluctuations, rather than evolved products of a long causal history. Because we clearly live in a consistent world with corroborated records and causal chains, many researchers take this as a constraint on cosmological models. A successful cosmology should avoid making Boltzmann brains the generic observer. How to avoid that problem? One approach is to change the long-term structure of the universe so that true thermal equilibrium is never reached, or so that the number of observers produced by fluctuations remains negligible compared with ordinary observers produced during eras of low entropy. If dark energy decays or changes in a way that prevents eternal de Sitter equilibrium, that can help. If the multiverse picture has some selection effect or measure that weights histories differently, that might also shift the balance. There's no single agreed-upon solution yet, which is part of what makes this an active area of research. But the Boltzmann brain thought experiment is useful because it turns abstract thermodynamic reasoning into a testable-seeming constraint on cosmological ideas. Speaking of the multiverse, that concept pops up frequently in discussions of low-entropy beginnings and cosmic endings. If our observable universe is just one region in a much larger, possibly infinite ensemble of regions with different physical properties, then the existence of a low-entropy patch like ours might be explained statistically. Only rare pockets start in a low-entropy configuration, and only in such pockets can complexity and observers evolve. That's a kind of selection argument. It's neat because it uses the same statistical intuition that explains why cream mixes into coffee rather than unmixes. But it also raises new problems about how to define probabilities in an infinite ensemble and how to avoid self-undermining predictions like the Boltzmann brain issue. Multiverse proposals can be powerful explanatory tools, but they push the puzzle of why low entropy to the larger context of the multiverse rather than solving it in a final way. Let's pull back to a more grounded issue: the arrow of time. We've seen that entropy increasing gives us a direction for time, past to future, because processes that spread energy and increase entropy are overwhelmingly likely compared with their time-reversed counterparts. But why was the early universe in a low-entropy state to begin with? That question sometimes goes by the label, the past hypothesis. It's the claim that the universe started in a special boundary condition, low entropy at or near the Big Bang. That boundary condition, combined with time-symmetric microscopic laws, produces the macroscopic arrow we experience. Some physicists take the past hypothesis as a brute fact. The universe simply started in a very special state, and that's an initial condition we need to accept. Others seek dynamical explanations. Inflation, a brief episode of extremely rapid expansion in the early universe, helps explain why the cosmos looks so smooth and uniform on large scales. That smoothness correlates with low gravitational entropy in certain senses, but whether inflation actually explains the low overall entropy is debated. Inflation seems to require an initial patch that's smooth enough to begin with, so you may have traded one special initial condition for another. There are proposals that place the low entropy condition at a different temporal boundary. For example, symmetric models that have a low entropy region in the middle and increasing entropy in both time directions from there. But these models are speculative and face their own conceptual hurdles. Another thread links entropy and information more explicitly. In thermodynamics, entropy measures missing information about microscopic details. In computation and information theory, erasing information has a thermodynamic cost. Landor's principle states that erasing one bit of information dissipates at least kT ln2 of energy as heat, where T is the temperature of the environment. This isn't a fanciful law. It's a physical connection between information processing and the thermodynamic arrow. The implication is that any system that stores and processes information, including brains and computers, must pay an entropy price. As the universe heads toward heat death, the opportunities to erase information and so to process information in useful ways shrink. That ties the thermodynamic end of the universe to limits on computation, memory, and the persistence of minds if they rely on physical processes. Freeman Dyson once asked whether life could persist forever by slowing down its metabolism and stretching subjective time. If organisms operate ever more slowly, perhaps their subjective experiences could last unboundedly even with dwindling resources. Back in the 1970s, this was an intriguing idea under the assumption that the universe expands, but remains matter-dominated and cooling slowly. Dyson sketched ways organisms might hibernate and wake periodically, squeezing more utility out of finite resources. But later discoveries changed the backdrop. With cosmic acceleration driven by a cosmological constant, there's a minimum temperature, the de Sitter temperature, below which you can't cool, and horizons isolate regions so that you can't indefinitely gather more energy. Work by Cross, Starkman, and others argued that in a universe dominated by a cosmological constant, Dyson-style indefinite survival isn't possible. The presence of a de Sitter horizon and a finite temperature imposes caps on the total amount of usable energy and information processing. So whether life or computation can persist forever depends sensitively on dark energy's nature. Black holes, which earlier we noted are huge entropy reservoirs, add another twist to the survival and information stories. If you want to extract energy very far in the future, black holes offer a last source. They evaporate via Hawking radiation, releasing energy that could in principle be harvested. A wise civilization could sit near an evaporating black hole and use its Hawking radiation to power computation or survival in the far future. But there are practical and theoretical constraints. The power per unit time from a very massive black hole is tiny until near the end of its life when emission grows. And the rates and timing are such that there are limits to how much you can extract over arbitrarily long durations. Moreover, if the global background is de Sitter, horizons and isolation again restrict long-term gathering of resources. Still, in universes without a positive cosmological constant, black holes become even more attractive as late-time energy sources and might extend the era of structured activity. Now let's look at more radical escape routes from heat death. One family of ideas imagines that our universe is not the end of the story, but can spawn new universes, baby universes, through processes like quantum tunneling or gravitational collapse. If it's possible to nucleate a region that inflates into a new universe, then there's a kind of cosmic natural selection in which new low-entropy patches are born. These baby universes would be causally disconnected from their parent, so they don't help anyone in the original universe directly, but they change the overall space of possibilities. Some theorists have even speculated about deliberately creating new universes in the lab, using enormous energies to seed an inflationary bubble. These ideas are far out and rest on theoretical extrapolations of quantum gravity we don't yet control, but they show how the heat-death picture could be sidestepped in principle if the laws of physics allow creation of fresh, low-entropy spacetimes. Penrose's conformal cyclic cosmology, CCC, is another bold alternative. Penrose proposes that the remote, ultra-emptied future of one universe can be conformally reinterpreted as the low-entropy Big Bang of the next, setting up a sequence of eons. The key move is mathematical. If you stretch out the scales so that massless degrees of freedom dominate and masses become irrelevant, the infinite future of one eon can be matched to the Big Bang of a successor eon. CCC is speculative and controversial, and it makes specific observational claims about subtle imprints in the cosmic microwave background that are under study. If true, CCC would replace heat death with a kind of eternal chaining of universes, each arising from the previous one's cold ashes. It's an example of creative thinking about how the arrow of time and low-entropy beginnings might be reassigned across cycles. A related approach is to consider bouncing cosmologies. Instead of a one-shot Big Bang followed by endless expansion or heat death, the universe might undergo repeated cycles of contraction and bounce. In such models, entropy issues become acute. Entropy must be removed or reset at each bounce, because otherwise each new cycle would start with higher and higher entropy, and the cycles would lose structure quickly. Some models attempt to address entropy by proposing mechanisms that dilute entropy between cycles, or convert it into degrees of freedom that don't affect the next cycle's conditions. These proposals are mathematically intricate and often rely on aspects of quantum gravity or modifications of general relativity. They offer a conceptual alternative to the single-run heat-death story, but they're far from settled. A recurring theme is that our deepest uncertainties about the future link back to our uncertainties about fundamental physics. What is dark energy? How does gravity quantize? And how do horizons and entropy work in quantum gravity? The holographic principle, born from studies of black holes, suggests that the information content of a region of space is proportional to the area of its boundary, not the volume. Applied to cosmology, holography suggests that spacetime and gravity might be emergent from more fundamental, lower-dimensional degrees of freedom. If that's true, then entropy and the counting of microstates in the far future could be very different from our naive extrapolations. For example, if de Sitter space corresponds to a finite-dimensional Hilbert space in the true theory, that would explain the finite entropy associated with cosmological horizons. But building a complete quantum theory of de Sitter space has proved challenging. Most successful holographic constructions work best for spacetimes with negative curvature anti-de Sitter space, not positive curvature de Sitter space. This technical difficulty matters because without a firm understanding of quantum de Sitter space, extrapolating ideas about recurrences, Boltzmann branes, and ultimate entropy limits is tentative. One more conceptual tool worth visiting is the role of coarse graining. When we talk about entropy increasing, we're implicitly making choices about what microscopic details we care about and what macroscopic features we track. Entropy depends on the partitioning between micro and macro. If you choose fine-grained variables that capture every microscopic detail, the entropy can be constant under reversible dynamics. It's only when you coarse grain, i.e., treat many microscopic configurations as equivalent, that entropy can increase. That's exactly what happens in everyday thermodynamics. We don't track each molecule's position and momentum. We track temperature, pressure, and density. The interesting question for cosmology is what the natural coarse graining is and whether there are physically preferred ways to split micro from macro. In systems with gravity, the choices can be subtle because gravity itself produces structures over many scales. Debates about what counts as entropy in cosmology, matter fields, horizons, gravitational degrees of freedom, hinge on how coarse graining is done. Let's also say a word about the experiential angle. What does heat death mean for beings that define their lives through change? Life, memory, and agency are processes that take low-entropy resources and convert them into work and information-bearing patterns. Memory itself is a physical pattern maintained by an ongoing expenditure of free energy and repeated erasure and rewriting of information. If free energy disappears, maintaining memories becomes impossible, records decay, and histories become inaccessible. From an embedded observer's perspective, time is the sequence of memories and causal traces. If those traces can no longer form or be sustained, the experienced flow of time dissolves into a static background. That doesn't mean the time parameter in the equation stops. It means there's nothing left to mark its passage. Because of all these entangled threads, dark energy's nature, horizon thermodynamics, quantum gravity, Boltzmann brains, and information processing limits, the question, could the universe freeze forever, resists a single answer. In some straightforward extrapolations, yes, usable energy runs out and we get an effectively frozen cosmos. In other directions, new physics or cosmological models open doors to cycles, baby universes, or evolving dark energy that sidestep the freeze. And some of the most profound puzzles, why the universe began in low entropy, what the right measure over cosmological histories is, and how to count observers, remain open. That might sound like an embarrassment of options, but it's also a sign of a healthy scientific frontier. When we stretch known laws to their extremes, the seams of our understanding show. Those seams guide where to look next. For instance, measurements that pin down the equation of state of dark energy more precisely could tell us whether the cosmological constant is stable, or if something time-varying is at work. Observational searches for subtle patterns in the cosmic microwave background, or in the distribution of galaxies, can test cyclic or bounce models. Theoretical progress in quantum gravity and holography might finally give a clear account of de Sitter horizons and their microscopic degrees of freedom, settling debates about the universe's finite or infinite information capacity. Meanwhile, the intellectual connections between cosmology and computation keep feeding into one another. Limits on computation set by cosmology are not purely philosophical. They constrain what future civilizations could in principle accomplish. Conversely, thinking about the resources needed to perform certain physical experiments or to manipulate spacetime informs what sorts of cosmological scenarios might be physically meaningful or testable. It's a loop where abstract physics has implications for the very concrete issue of what processing power and memory are physically doable in extreme spacetimes. There's also a human element worth acknowledging. These cosmic fates, heat death, big rip, vacuum decay, cyclical universes, are remote and, in practical terms, irrelevant to the day-to-day concerns of planetary life. Yet they matter intellectually because they probe the consistency of our physical theories. They tug on foundational questions. What does it mean for something to be possible but practically impossible? How should we assign probabilities to events in an effectively infinite cosmos? How do we define observers and payoffs in a setting where copies and fluctuations can appear? Grappling with these questions sharpens our tools in other areas of physics, from black hole information to the thermodynamics of small quantum machines. Let's step back and make a small list of the types of futures that physicists talk about, and the core reasons they matter, just to keep the landscape tidy in your head. Heat death, big freeze. The cosmic engine runs down. Entropy approaches a maximum under current conditions. No usable gradients remain. It's the straightforward thermodynamic endpoint if dark energy behaves like a cosmological constant, or if nothing else intervenes to create new low-entropy patches. Big rip if the dark energy density increases without bound. Expansion accelerates so violently that bound structures are torn apart at a finite time. It's dramatic and potentially singular, depending on details of the underlying physics. Vacuum decay. A quantum tunneling event could convert our vacuum to a lower energy vacuum, changing the laws or constants of physics inside the expanding bubble. It's sudden and locally catastrophic, although the bubble's expansion proceeds at the speed of light, so there's no warning from within. Eternal inflation and the multiverse. If inflation never completely ends globally, different regions can thermalize into different pocket universes with varying properties. This creates a vast landscape of possible physics and pushes the low-entropy question into a statistical framework. Cyclic or bouncing models. The universe goes through repeated phases, potentially avoiding a one-time freeze by resetting or redistributing entropy between cycles. These models require mechanisms to remove or reset entropy and are theoretically demanding. Baby universe production. A parent universe spawns new, low-entropy universes via quantum processes. This changes the global bookkeeping, but leaves the parent's fate unchanged for its inhabitants. Recurrence and fluctuation-dominated futures. In finite entropy settings, recurrences and rare fluctuations, including Boltzmann brains, become inevitable over stupendous timescales, forcing us to confront how to weigh such occurrences in our probabilistic reasoning. Each option has different consequences for observers, for the possibility of indefinite computation or survival, and for the fundamental laws needed to describe them. And each option links back to empirical and theoretical questions we can, in some cases, test or sharpen. If you're picturing a single dramatic image, a frozen clock, a stopped heart, sunlight locked in place, that picture captures some emotional truth. Many familiar processes depend on gradients and change, and if those evaporate, our kind of life cannot persist. But the cosmic answer is not a single fixed picture. It's a branching tree of possibilities, each branch governed by specific facts of physics we still need to pin down. The wonderfully frustrating thing about cosmology is that even when we don't yet have the final answers, the constraints we do have, from the cosmic microwave background, from supernova surveys, from black hole thermodynamics and quantum field theory, let us rule out swaths of the possibility space and focus our imagination where it's both productive and testable. So where does that leave us practically? For humans today, studying these questions drives progress in physics. Measurements that constrain dark energy more tightly, experiments that probe quantum gravity regimes, and theoretical advances in statistical mechanics and information theory are all steps that illuminate the eventual fates available to the cosmos. And philosophically, tackling the end of time helps clarify what we mean by time in the first place. Is it a fundamental backdrop, an emergent bookkeeping device, or simply the name we give to sequences of change that are only meaningful insofar as records and memories persist? Wrestling with those questions is as much about sharpening our concepts as it is about predicting destinies 10–100 years hence. The next natural thing to dig into is the early side of the story. If the arrow of time depends on a special low-entropy beginning, what mechanisms could have produced that beginning? Exploring that question draws together inflation, quantum cosmology, and speculative ideas about information and spacetime emergence. It's where origins and endings meet, because understanding why entropy started low may be the key to knowing whether the universe's apparent arrow will ever reverse, repeat, or be reset in ways we can't yet imagine. We left off with the idea that the arrow of time, the reason cause seems to precede effect and why eggs scramble but never unscramble, ultimately comes from the universe beginning in a very special, very low-entropy state. That's the past hypothesis in a nutshell. The next natural question is, how did the universe get that special start? Was it a brute fact we have to accept, or could there be a dynamical explanation, a physical process that naturally produces the kind of smooth, low-entropy beginning we need? Let's unpack the main ideas physicists have explored and the puzzles each one faces in an accessible way. Start with the thing we know best from observations. The early universe was extraordinarily smooth. The cosmic microwave background, that faint glow left over from when the universe was about 380,000 years old, is uniform in temperature across the sky to 1 part in 100,000. That tiny variation is precisely the signal that later grew, under gravity, into galaxies and stars. Smoothness at early times is exactly what it means for the universe to be low in gravitational entropy. Instead of having matter already clumped into black holes or dense lumps, which would be the gravitationally high-entropy state, mass and energy were spread out almost uniformly. It looks ordered, and in the gravitational sense it was ordered. There were few microscopic ways to realize that particular large-scale smooth pattern compared with all the clumpy possibilities. This flips the usual everyday intuition about entropy. For a gas in a box without gravity, evenly spread out is high entropy. For gravity, the opposite is true. Clumping tends to increase entropy because gravitational collapse can form black holes, and black holes carry enormous entropy. To visualize this, imagine you have 1,000 identical balls in a shallow bowl that attracts them toward the center. If they all sit gently on the rim, that's a very special configuration. But if they've rolled into a heap in the center, there are myriad microscopic arrangements that look like a heap. Gravity encourages that heap, and the heap is the generic, high-entropy state. The smooth early universe is the reverse situation, rare and special. Inflation is the most widely known attempt to explain how that special smoothness could arise dynamically. The idea is that, very early on, the universe underwent a brief epoch of extremely rapid expansion. A tiny patch of space that was already somewhat homogeneous got blown up to a size larger than the observable universe today. Quantum fluctuations during inflation were stretched and turned into the tiny irregularities that became galaxies later. Inflation explains several observational facts neatly. The large-scale uniformity of the cosmic microwave background, the near flatness of space, and the specific statistical properties of the primordial fluctuations. They're nearly scale-invariant, approximately Gaussian, and of the amplitude we observe. That's why inflation is the leading story for the early universe in modern cosmology. But there's a subtler issue. Did inflation really make the problem of low initial entropy go away, or did it just push the specialness back a step? Critics point out that to start inflation you still need a patch of space that can undergo that exponential expansion. A patch that is smooth enough and has the right energy conditions. In other words, inflation requires a low entropy-ish set of initial conditions to begin with. Some defenders argue that inflation exponentially stretches whatever initial region is present, so even a relatively small and not very special patch can inflate and produce a large smooth region. Others, including Roger Penrose in particular, respond that an inflating patch is itself very special when judged against the full set of possible gravitational initial conditions. Penrose has emphasized that the deep problem is gravitational, the early universe's near absence of tidal distortions, something formalized in his Weyl curvature hypothesis, is a low-entropy gravitational condition that inflation doesn't obviously make generic. So what might a more complete solution look like? Several broad classes of ideas have been proposed. One family accepts the past hypothesis as a boundary condition, a law-like initial condition, and asks what consequences it has. Another family looks for dynamical mechanisms that either produce low entropy from generic states or create circumstances where entropy can be effectively reset. A third group tries to redefine the problem by changing what we mean by entropy or by casting spacetime and time itself as emergent from deeper quantum information structure. Let's walk through these avenues with examples and some intuition. First, the boundary condition approach. We could simply elevate the universe began with very low gravitational entropy to a fundamental postulate. It's awkward philosophically. It feels like putting something unexplained into the laws, but it's logically consistent and pragmatic. If you accept it, a lot of thermodynamic reasoning flows straightforwardly. Entropy increases after that starting point, giving us a clean arrow of time. Some physicists find this uncomfortable because it's unsatisfying. Why should nature pick that special boundary? But there's nothing in the mathematics of the laws themselves that forbids treating an initial low-entropy condition as a basic fact of cosmology. Next, dynamical proposals. One way to try to generate low initial entropy is to have a prehistory that naturally smooths space. Inflation is the main dynamical candidate, but there are other models too. The ekpyrotic or cyclic models, inspired partly by ideas in string theory, propose that our current expanding phase was preceded by a slow contraction. During this slow, special kind of contraction, anisotropies and inhomogeneities are damped out, leaving the universe very smooth at the bounce that leads into the expanding phase we inhabit. In this picture, low entropy isn't an unexplained starting condition. It's the outcome of the special contractive dynamics. Ekpyrotic models have virtues. They can, in principle, reduce the need for finely tuned inflationary initial patches. But they must also contend with issues of entropy through the bounce. Where does the entropy go, and how does the model avoid simply passing accumulated entropy forward? These are active technical questions involving quantum gravity. Another dynamical route is to imagine the universe as part of a larger multiverse in which regions with different properties constantly nucleate. In some versions of eternal inflation, tiny regions fluctuate into states that then inflate and produce their own pocket universes. If the space of possible initial conditions is vast, it could be that low-entropy patches like ours are rare but inevitable somewhere. We would then explain our observations by a selection effect. We find ourselves in a rare low-entropy pocket because only such pockets permit observers. That's an anthropic-style argument. It shifts the question from why did this particular patch begin low entropy to why do we observe low entropy? Because only observers in such patches could exist. The multiverse option raises its own technical headaches, though. When you have an effectively infinite ensemble of pockets, comparing probabilities becomes tricky, the measure problem, and you run into the Boltzmann brain worry in new forms. If fluctuations in an eternally inflating background can produce observers through random chance, then counting how many ordinary observers arise through long evolutionary histories versus how many fleeting fluctuation observers appear becomes a thorny exercise. A different tack is to rethink what entropy counts in the first place. In ordinary thermodynamics, entropy measures how many microscopic configurations correspond to a given macroscopic state. But when gravity is present, what counts as a microstate is subtle, and horizons complicate the bookkeeping. The holographic principle, born in black hole physics, suggests that the information content of a region is proportional to the area of its boundary, not its volume. That invites the thought that spacetime geometry and even time might be emergent from more fundamental, possibly lower-dimensional degrees of freedom. Under that point of view, the early universe's low entropy could be a statement about the initial pattern of entanglement among those fundamental degrees of freedom. Some modern work links the growth of entanglement to the emergence of classical spacetime geometry. When entanglement patterns change, geometry changes with them. If time is in some sense tied to the growth of entanglement or the spreading of quantum correlations, the arrow of time could be explained by an initial condition of low entanglement that then increases. That reframes low entropy beginning as initially simple entanglement structure, rather than as a brute geometrical fact. These are exciting ideas because they connect thermodynamics to quantum information, and they hint at how a microscopic theory of spacetime might naturally produce a direction for time. But they're still speculative and mathematically challenging. Let's return to inflation and look at one particularly interesting detail. Inflation doesn't leave you with a cold, empty universe. At the end of inflation comes reheating, when the energy driving inflation decays into ordinary particles, filling space with a hot plasma and producing an enormous amount of entropy. That entropy, however, is not the gravitational entropy that Penrose highlights. The reheating-produced radiation has very high thermodynamic entropy for the matter fields, but the gravitational configuration after reheating is still smooth on large scales. So the kind of low gravitational entropy we need to explain the arrow of time can persist even as matter entropy becomes large. Inflation thereby neatly explains how you can get a hot, high-entropy for matter universe that is still very low in gravitational entropy, allowing a long period of entropy increase that produces stars, life, and structure. A curious flip side is that inflation itself generates the primordial density fluctuations from vacuum quantum fluctuations. These quantum fluctuations are tiny and nearly Gaussian, meaning the probability distributions are bell curve-like, and inflation stretches them to macroscopic scales. These seeds are, in a sense, low-information initial perturbations that evolve under gravity into all the complexity we see. So inflation builds the seeds of structure from the quantum vacuum. That's partly why inflation is so elegant. It transforms quantum uncertainty into classical structure. But the story is messy in the details. The so-called initial quantum state of fluctuations during inflation is usually taken to be the Bunch-Davies vacuum, a particular minimal energy state, and that choice matters for the statistical properties of the perturbations. There are variations and alternatives that change predictions for non-Gaussianities and gravitational waves. Observational programs, satellites like Planck and future probes looking for primordial B-modes in the polarization of the cosmic microwave background, are trying to detect the gravitational wave imprint of inflation. A detection would strongly support inflationary dynamics and give us a handle on the energy scale at which inflation occurred, with implications for entropy accounting. Conversely, tighter non-detections constrain inflationary models and push theorists toward specific potentials or alternatives. Penrose's alternative, the Weyl curvature hypothesis, is worth spelling out intuitively. In general relativity, the curvature of spacetime has different parts. Some parts are directly tied to the energy and matter content Ricci curvature, and other parts encode tidal distortions and gravitational waves, Weyl curvature. Penrose proposes that the early universe's Weyl curvature was essentially zero, meaning the gravitational degrees of freedom were very quiet. That condition would produce low gravitational entropy because it forbids the kind of tidal wrinkling and clumping associated with black holes. From that perspective, the initial low entropy is a geometrical boundary condition. The universe began with a nearly vanishing Weyl curvature. Penrose then speculates about ways this could connect to conformal cyclic cosmology, CCC, the idea that the far future of one eon becomes, after a geometric rescaling, the Big Bang of the next, linking eons in a chain. CCC tries to replace a brute initial condition with an ongoing cycle, where the special low-entropy boundary at each new beginning has geometric meaning tied to conformal structure. CCC is bold and controversial. It makes specific claims that can be tested, e.g., possible imprints in the cosmic microwave background from black hole collisions in prior eons, and those predictions are under active scrutiny. There are also proposals that seek to derive the past hypothesis from the statistical mechanics of cosmological degrees of freedom. For instance, some authors have explored whether typical states in certain gravitational phase spaces have the characteristic that low-entropy smooth regions are more likely to spawn inflating patches than high-entropy clumpy ones. The idea here is subtle. Rather than asking about the probability of a completely smooth universe, one asks whether inflation acts as an attractor in the space of possible initial conditions, so that a wide array of starting configurations naturally evolve into an inflating region. The verdict here is mixed. Inhomogeneous and anisotropic initial data can sometimes fail to inflate. In other cases, inflation can commence in interestingly generic ways. The detailed answer depends sensitively on the model, the type of matter or fields present, and the precise meaning of generic in an infinite-dimensional space of geometries. Quantum cosmology offers another angle. In quantum mechanics, states are described by wave functions, and one can try to write a wave function of the universe. The Hartle-Hawking no-boundary proposal imagines that the universe's wave function is computed by a path integral over compact Euclidean geometries. In a hand-wavy picture, the universe rounded off in the past rather than having a boundary singularity. The proposal is intended to supply a natural selection of initial conditions that favor smooth beginnings. Alternatively, Vilenkin's tunneling proposal gives a different boundary condition and different weights to inflationary initial states. These are mathematically subtle and contested constructions, but the key point is that quantum cosmology might provide a probabilistic rule for which initial geometries are favored. Whether it actually predicts what we observe is still under debate. Results depend on technical choices and measure issues, and critics worry about hidden assumptions and ambiguities in how to interpret quantum probabilities for the universe as a whole. There's also a fascinating set of ideas that tries to explain the arrow of time by making it emergent from a larger, time-symmetric background. Carroll and Chen proposed a picture in which the universe as a whole is eternally existing with no preferred direction, but entropy increases away from a low entropy, bounce, region in both time directions. The idea is that you could have a central region of low entropy that gives rise to two opposite thermodynamic arrows of time, one pointing to the future on our side, and one pointing to the future on the other side, which would be our past if you looked from their perspective. In this setup, there's no special initial moment singled out overall. Instead, the specialness is localized and entropy increases away from it. It's a radical way of avoiding a unique initial condition, but it faces challenges about how such low entropy central regions are produced and whether they are themselves natural outcomes of the underlying dynamics. All these proposals sit against an observational backdrop that is increasingly precise. Measurements of the cosmic microwave background, the large-scale distribution of galaxies, and constraints on primordial gravitational waves are powerful tools. They don't directly tell us why the universe started low entropy, but they narrow the set of viable models for the early universe and thus indirectly shape which explanations are plausible. For instance, if primordial gravitational waves were detected at a level corresponding to a very high inflationary energy scale, that would push models towards certain classes of inflation potentials and might favor a simple inflationary origin for the observed smoothness. Conversely, if such waves remain elusive, small field inflation models or alternatives gain traction. We should also mention the Higgs and vacuum stability, because the question of whether our vacuum is metastable feeds into long-term cosmology. Current measurements of the Higgs boson mass and the top quark mass suggest that the standard model vacuum might be metastable. It's not the lowest energy configuration possible, but is long-lived on timescales enormously longer than the current age of the universe. If that metastability is real, it makes vacuum decay a possible, though extremely unlikely in the near-term future event. That possibility doesn't directly resolve the past hypothesis, but it adds a twist to the long-term fate of the cosmos and demonstrates how particle physics and cosmology interplay. Another conceptual pivot is to connect entropy and the arrow of time to quantum measurement and decoherence. The classical world we experience arises from quantum systems constantly interacting with their environments. Photons scatter, molecules collide, and quantum superpositions decohere into effectively classical mixtures. Decoherence increases entropy because it spreads information about a system into many environmental degrees of freedom that we don't track. Some researchers argue that the arrow of time is intimately tied to this ubiquitous process. In an initially low-entropy universe, systems start in states with low entanglement with their environments, and decoherence builds entanglement and increases entropy as time goes on. In such a view, the initial low-entropy condition is low entanglement, and the classical world, with its definite outcomes and records, is a natural consequence of entanglement growth. Emergent time ideas go even further, suggesting that time itself may not be a fundamental parameter in the deepest laws. In some approaches to quantum gravity, particularly those under the umbrella of holography, time and space appear as effective descriptions emerging from patterns of quantum entanglement. If so, then the arrow of time could be tied to the direction in which entanglement becomes more complex, or in which a statistical ensemble of microstates grows. These are cutting-edge, mathematically challenging proposals, but they're attractive because they promise to link the thermodynamic arrow with the emergence of spacetime itself. Through all this, a recurring theme emerges. Entropy and time are deeply entangled with our deepest uncertainties about gravity, quantum mechanics, and cosmology. The past hypothesis pinpoints where the mystery sits. If the laws are symmetric, then the asymmetry must come from boundary conditions somewhere. Whether that boundary condition is just a fact about the way the universe is, or can be derived from dynamics, remains an open and stimulating question. Practical experiments and observations continue to chip away at the possibilities. Searches for primordial non-Gaussianity, measurements of the scalar spectral index, how the amplitude of primordial fluctuations depends on scale, constraints on isocurvature modes, and increasingly precise maps of large-scale structure, all narrow inflationary or alternative model space. On the gravitational side, studies of black hole thermodynamics, quantum corrections to horizon entropy, and attempts to construct a consistent quantum theory of de Sitter space are pushing the frontier of what we can say about cosmic entropy at the most fundamental level. There's also a philosophical angle worth noting. Some physicists and philosophers argue that the past hypothesis should be treated on par with the laws of thermodynamics. It's a global constraint on allowable histories, not derived from dynamics but necessary to make sense of observed regularities. Others resist such a move, preferring explanations that make the low entropy beginning a consequence of deeper principles. Either way, the debate sharpens our understanding of what physicists mean by laws versus initial conditions, and why cosmology sits at the boundary of physics and metaphysics. To keep things concrete, imagine two thought experiments. First, picture an isolated box with gravity turned off. Put all the gas molecules crammed into one corner. That's a low entropy configuration, and left alone the gas will disperse and increase entropy. Now switch gravity on and imagine the molecules attract each other. Over time, they'll clump and eventually might form a compact object analogous to a black hole, which would be a high-entropy end state. The early universe resembles the first box with a key twist. Because gravity was crucial, the smooth distribution of matter then was a very special kind of low entropy. Explaining why we started in the neat corner case, the low entropy initial setup is the big puzzle. Second, imagine trying to define a clock in a universe that has reached maximum entropy. Your clock needs a process. Hammering, oscillating atoms, the ticking of a pendulum, all of those need free energy. In a heat-dead universe, no such processes exist. The arrow of time for any internal observer disappears because nothing changes in a sustained, ordered way. The existence of an arrow now, the fact that we can make records, run experiments that reliably produce consistent outcomes, and talk about cause and effect, relies on that earlier special initial state that set up a long uphill slope of entropy increase for complexity to develop and survive. All these threads, inflation and its critics, bouncing and cyclic models, quantum cosmology proposals, emergent time ideas, and multiverse selection effects, are different ways of wrestling with the same conceptual knot. The fact that time seems to have a direction depends on a seemingly unlikely beginning. Progress is being made in many directions, but a fully satisfying, widely accepted account that explains why the early gravitational degrees of freedom were so quiet and why entropy started low remains one of the deepest puzzles in theoretical physics. That unresolved character is not a failure. It's what makes the question rich and fertile. It draws together observations across cosmology, deep results from black hole thermodynamics, insights from quantum information, and foundational questions about what we mean by the laws of nature. As research pushes forward, new observations could tip the balance. A detection of primordial gravitational waves at a certain amplitude would strengthen specific inflationary models. A null result at certain sensitivity levels constrains them. Evidence for subtle anomalies in the cosmic microwave background that match cyclic or pre-Big Bang imprints would bolster alternatives. Theoretical breakthroughs in quantum gravity that clarify how to count microstates for de Sitter horizons, or that show how spacetime emerges from entanglement in a way that naturally picks out low entanglement initial conditions, would reshape the debate. Until then, the past hypothesis stands as a milestone, a clear, simple statement of the problem that any full cosmological theory needs to address. So when we ask, more broadly, could time stop, Or could the universe freeze forever? We find the answer is layered. The prospect of a heat-dead, gradient-less future is a robust prediction of many standard extrapolations. But whether that scenario is final, avoidable, or even the right conceptual framing depends on those earlier puzzles about the origin of the arrow of time. The way the universe started constrains how it can end, and conversely, thinking about possible endings helps us focus on what would have had to be special at the beginning. That's why probing the very early universe isn't just about origins, it's about destinies too. If the fate of the cosmos hangs so close to details of dark energy, black holes, and the universe's initial state, a natural next question is, how do we actually test any of this? What can we measure now or in the coming decades that would let us prefer one long-term story over another? Fortunately, cosmology is an empirical science, and a surprising amount of the future hinges on measurements we can realistically make today or in the next generation of instruments. One of the clearest observational levers is the behavior of dark energy. In simple terms, cosmologists often characterize dark energy by a number called W, which relates the pressure dark energy exerts to its energy density. If W equals -1 exactly, the simplest interpretation is a cosmological constant, a fixed energy density that doesn't change as the universe expands. That case naturally tends toward a de Sitter future. Exponential expansion, a finite temperature for the cosmic horizon, and the kind of thermal endpoint behavior we've been talking about. If W is not exactly -1 and instead varies with time, that opens up alternatives. A value slightly higher than -1, W-1, corresponds to quintessence-like scenarios where the energy density may dilute or evolve. A value less than -1, W-1, points toward phantom energy, which can drive a big rip if the effect grows unchecked. Measuring W precisely is a high-priority program in observational cosmology. We do this with multiple complementary tools. Supernovae act as standard candles that tell us how expansion has changed over time. Baryon acoustic oscillations, regular, large-scale wiggles imprinted in the distribution of galaxies, provide a standard ruler. Weak gravitational lensing measures how matter bends light and constrains how structure grows under gravity. All these probes are being pushed to higher precision by surveys such as the Dark Energy Spectroscopic Instrument (DAISY), the Vera Rubin Observatory, which will run the Legacy Survey of Space and Time (LSSD), the European Space Agency's Euclid mission, and NASA's Nancy Grace Roman Space Telescope. Improved cosmic microwave background experiments, like CMBS-4, also add power through tighter constraints on geometry and early universe physics. What these observations can do is rule out large deviations from W equals -1 and begin to detect trends if the dark energy density is evolving. If we end up pinning W to -1 to high precision with no time evolution, that strengthens the case for a de Sitter-like future and the kinds of thermal horizon considerations that imply an eventual practical freeze-out. If instead evidence grows that W changes over time or that dark energy decays, then heat death as typically sketched might be avoided or significantly altered. The data may not give us a complete guarantee about the distant future. There could always be slow drifts or late time transitions, but narrowing the possibilities matters greatly for the big picture conclusions. Another measurable handle on cosmic destiny comes from particle physics. The stability of the vacuum, the particular arrangement of quantum fields in which we live, affects whether vacuum decay is a live possibility. Given current measurements of the Higgs boson mass and the top quark's mass, the Standard Model by itself seems to place our vacuum in a metastable region. A false vacuum that could, in principle, tunnel to a lower energy true vacuum. The probability of a catastrophic bubble forming depends sensitively on precise values of those masses and on unknown physics at high energies. So improving our measurements at particle colliders and building a better understanding of the Higgs potential could alter the odds. Future collider experiments, more refined top mass measurements, and theoretical work on high-energy completions of the Standard Model will sharpen whether vacuum decay is an abstract possibility or a genuine constraint on the far future. Black holes offer another observationally relevant axis. The more we learn about how black holes form, merge, and behave, the better we can estimate how much entropy sits locked in event horizons, and how that entropy will be redistributed as black holes evaporate. Gravitational wave astronomy, inaugurated by LIGO, and now expanding with instruments like Virgo and KAGRA, and planned space missions like LISA, gives us direct information about black hole populations and their masses. Those mass distributions feed into long-term forecasts of how many massive black holes will dominate entropy counts and how long they will take to evaporate. The theoretical side, understanding Hawking radiation and black hole thermodynamics in detail, perhaps with inputs from quantum gravity, is equally important for pinning down the late-time bookkeeping of entropy. There's also a surprising degree to which tabletop and laboratory experiments speak to the conceptual foundations we're relying on. Landor's principle, the minimal thermodynamic cost of erasing a bit of information, was once merely a thought experiment, but it's now been tested in precision experiments with single bits and small systems. Experiments that implement Maxwell's demon with feedback control, that measure fluctuations of work in tiny heat engines, and that probe thermodynamic behavior of quantum systems all help refine our understanding of irreversibility, how coarse graining leads to entropy increase, and how information links to thermodynamic cost. Those lessons scale up conceptually. If we misjudge the thermodynamics of tiny systems, we could be misled about the limits of computation or memory far into the future. Getting the microphysics right is important even when thinking about cosmic endurance. All of which leads to the question, could any civilization, even an incredibly advanced one, do anything to change the universe's ultimate freeze? There's a long tradition of thoughtful speculation on this, and the answers are sobering but scientifically illuminating. Freeman Dyson famously wondered whether life could persist forever by progressively slowing subjective processes as the universe cooled, and by arranging hibernation cycles that conserve energy while keeping experience alive. Dyson's idea assumes a universe that keeps giving you arbitrarily low background temperatures and where you can exploit ever lower energy differences. Once we understood dark energy more firmly, especially the idea of a cosmological constant yielding a minimum de Sitter temperature, those hopes dimmed. If a finite background temperature and cosmic horizons impose absolute limits on cooling and on causal reach, then indefinite survival via Dyson's method is ruled out for universes dominated by a cosmological constant. Other proposals imagine extracting the last available energy from black holes. As black holes evaporate, their emitted radiation is an ultimate repository of usable energy. In principle, a civilization could orbit a black hole and harvest Hawking radiation, converting it to work or computation. Practically, the timescales for very massive black holes are so enormous, and the power outputs so tiny for most of their lives, that the net gains are limited. Also, if the background reaches a de Sitter temperature that exceeds the black hole's Hawking temperature, harvesting becomes impossible. So while black holes provide late-time resources, they don't open a route to eternity in the presence of a true cosmological constant. Some imaginatively bold ideas involve creating new, low-entropy regions, baby universes, artificially seeded inflationary bubbles, or engineered vacuum decays that spawn new spacetime patches. In principle, if you could nucleate a new inflating region and then jump into the resulting baby universe, you might escape your parent universe's heat death. But physics presently doesn't provide any practical protocol for such feats, and whether the causal structure allows travelers to carry information from the parent to the baby region is debatable. Theoretical studies of wormholes, bubble nucleation, and quantum gravity speculate about these moves, but deploying them requires control over Planck-scale physics that seems far beyond any plausible technological horizon. They are useful to think about because they show the sorts of things that would be needed to sidestep cosmic thermodynamic limits, but they remain speculative. A different tack, more conservative but still unsettling, is to consider which cosmological scenarios are self-consistent with the existence of ordinary observers like us. That's where the Boltzmann brain problem becomes a concrete criterion for preferring models. If a cosmological model predicts that, over its lifetime, random fluctuations producing isolated, self-aware brains vastly outnumber observers produced by long evolutionary histories, then that model is in tension with what we observe. A richly structured past, a shared cosmic history, and coherent memories. To avoid this, many cosmologists argue that viable models should ensure ordinary observers dominate the tally or that fluctuation-produced observers are suppressed. That requirement disfavors eternally old, thermalized de Sitter universes in which recurrences and rare fluctuations eventually dominate everything, unless there are measure theory ingredients that cut those possibilities down. That reasoning is not airtight. It mixes subtle probability and anthropic reasoning, but it provides a useful heuristic for comparing cosmological models. Digging deeper into the conceptual physics, one of the most active areas of modern research is the connection between entanglement and spacetime. Over the last decade or so, a line of work, motivated by string theory and the holographic principle, has suggested that spacetime geometry might emerge from patterns of quantum entanglement in a deeper microscopic theory. In those pictures, entanglement entropy and its growth play roles reminiscent of thermodynamic entropy in encoding gravitational dynamics. The idea can be made precise in certain negatively curved spacetimes via the ADS/CFT correspondence. The entanglement structure of a quantum field theory living on the boundary maps onto geometry in the bulk. If something like this extends to de Sitter space, the positive curvature geometry relevant for our observed accelerated expansion, then questions about horizon entropy, recurrences, and the ultimate information content of the universe could be recast in terms of quantum information theory. That reframing is promising for two reasons. First, quantum information gives us tools to think about coarse graining, what counts as a microstate, and how entanglement spreads, all the conceptual levers we need to handle entropy in a principled way. Second, experiments with engineered quantum systems, cold atoms, trapped ions, superconducting qubits, now let us watch entanglement grow and thermalization happen in a controlled way. These tabletop analogs can't recreate cosmology, but they test the principles connecting micro-level quantum dynamics with emergent, irreversible macroscopic behavior. If entanglement growth is the underlying mechanism of the arrow of time, these experiments will sharpen our intuition and might point toward mathematical structures we can attempt to lift into cosmological settings. Another technical but important piece of the puzzle is our understanding of de Sitter thermodynamics itself. A space with a positive cosmological constant, de Sitter space, has a temperature and associated entropy determined by the area of its cosmological horizon. The temperature is extremely small given our observed dark energy, roughly 10⁻29 to 10⁻30 Kelvin, depending on the precise constants you use. The corresponding entropy is enormous but finite, often quoted as on the order of 10⁻122 in natural units for the observable patch. Those are humbling numbers. A finite entropy means a finite-dimensional Hilbert space in the right theoretical framing, which in turn implies things like recurrences over unimaginably long times. But making that intuition precise requires a full quantum theory of de Sitter spacetime, and that remains an outstanding theoretical challenge. Most of our best understood holographic tools work for anti-de Sitter space with a reflecting boundary, not for positive vacuum energy cosmologies, so the frontier here is both technical and conceptually important. There's also a sharp distinction between microscopic reversibility and macroscopic irreversibility that's worth keeping front and center. The fundamental laws of classical mechanics, quantum mechanics without measurement collapse, general relativity away from singularities, are reversible in time. The reason we see an arrow of time is statistical. Certain microstates are overwhelmingly more likely given a low entropy boundary condition. That statistical explanation is robust, but it depends on what we count as microstates. Gravity complicates that bookkeeping by changing what configurations are typical. So much of the ongoing work is about specifying precisely what degrees of freedom matter for cosmic entropy. Is it just the matter fields? Does gravitational degrees of freedom, like the shape of space, count? What about horizon degrees of freedom? Answers to these questions shift the stakes for the future. All of these scientific discussions have philosophical consequences for how we think about time and meaning. If the experienced flow of time depends on the existence of records, memories, and maintained differences. If time, in a practical sense, is the procession of events a mind can register, then heat death represents an extinction of the kind of temporal experience we know. That's not a metaphysical annihilation of the parameter t in the equations. It's a loss of the physical structures that sustain narratives, causation, and experience. Philosophers of physics ponder whether that perspective undercuts certain arguments about cosmology. For example, whether probability statements about observers in the far future should be weighted in ways that respect subjective continuity and memory. Those debates can sound abstract, but they influence how cosmologists interpret paradoxes such as Boltzmann brains, and how they set criteria for acceptable models. It's worth mentioning in passing how some of these far-reaching cosmological and thermodynamic ideas feed back into practical technology. The thermodynamics of information is not just a curiosity. It sets limits on computation and underpins efforts to design low-power computing architectures. Landor's bound tells engineers that erasing information will cost energy in principle. That thermodynamic insight shapes how people think about reversible computation, adiabatic logic, and strategies for energy-efficient data centers. Experiments with tiny heat engines illuminate the limits of energy harvesting at nanoscale and inform the design of micro and nano devices. So the same physics that constrains the far future of the universe also constrains the design of future computers. A neat example of how grand theoretical questions can have down-to-earth consequences. Returning to cosmology, a promising empirical angle is searching for signatures that would distinguish cyclic or bounce models from inflation. Some versions of cyclic cosmology predict subtle imprints in the cosmic microwave background, perhaps particular non-Gaussian patterns, anisotropies, or certain gravitational wave signatures. Searching for those patterns is hard because the signals can be faint and subtle, but the data is getting better. Next-generation CMB experiments and large-scale structure surveys will probe these possibilities more tightly. If evidence for non-inflationary pre-Big Bang physics were found, it would revolutionize how we think about initial low entropy and could open ways for resetting entropy across cycles. Another observational frontier is the direct search for primordial gravitational waves, which, if detected and measured, would pin down the energy scale of inflation and constrain models. A high-energy inflationary phase, one with a large amplitude of primordial gravitational waves, would favor certain explanations for the smoothness of the early universe and would shape the entropy story at early times. Null results at improving sensitivities will narrow the allowed model space and may elevate alternatives. That's why investment in diverse observational programs matters. Each measurement removes or supports branches of the cosmic future tree. Let's spell out a specific example of how a single measurement could tilt the long-term picture. Suppose future surveys show that W is different from -1 and decaying, such that dark energy's density slowly decreases over cosmic time and eventually becomes negligible compared to matter and radiation. In that scenario, the universe might transition away from an accelerating phase in the distant future, allowing star formation to resume in principle or black holes to accrete new matter from the environment. The heat-death scenario that relies on eternal acceleration would be avoided. Putting numbers on that transition matters. How fast does W change? Over what timescale does dark energy dilute? The answers determine whether the change matters on timescales of 10-100 years or 10-20 years. Both are long, but one fundamentally alters the asymptotic behavior. Observations therefore give us leverage over whether the de Sitter-based freezeout is our best bet. At the same time, theory needs to keep pace. Some of the most profound constraints on long-term cosmology will come only when we have a sharper quantum theory of gravity and a clearer account of horizon microstates. If we could identify the microscopic degrees of freedom responsible for cosmological entropy, we could compute recurrence times, fluctuation spectra, and even the relative likelihoods of Boltzmann brains versus ordinary observers with more confidence. Right now, these are active frontiers. String theory, loop quantum gravity, causal set theory, and other approaches are attempting to build coherent frameworks. Each candidate theory changes the entropy bookkeeping and could, in principle, reshape our expectations for the far future. There's also an interplay between high-precision cosmology and foundational statistical questions. When you have extremely large or potentially infinite ensembles, either in time, very long-lived universes, or space, multiverses, assigning probabilities becomes delicate. Do you weight per unit volume, per observer, per historical trajectory? Each prescription can lead to dramatically different conclusions about what we should expect to find. Physicists studying these measure problems are not just playing with philosophy. They're trying to find prescriptions that avoid paradoxes like Boltzmann brains and that make testable predictions consistent with our observations. Progress here is slow but crucial. Outer future predictions depend on inner consistency of probability assignments. Given all these moving pieces, observations of dark energy, measurements of particle physics parameters, gravitational wave astronomy, quantum information theory, and quantum gravity, the path forward is necessarily multidisciplinary. Cosmologists and particle physicists, quantum information scientists, gravitational wave experimenters, and thermodynamicists all have parts to play. That convergence is one reason the questions are scientifically fertile. The same observations that help refine our view of the early universe also sharpen predictions about the late universe, and vice versa. If you imagine how this research program might evolve in the coming decades, a plausible roadmap emerges. Improved astronomical surveys will pin down the dark energy equation of state more tightly and might detect deviations or time evolution. Next-generation particle colliders and precision experiments will reduce uncertainties about the Higgs potential and top quark mass, clarifying the likelihood of vacuum decay. Gravitational wave catalogs will refine black hole demographics and test general relativity in strong field regimes. In parallel, experimental quantum information work will test ideas about entanglement, decoherence, and thermalization that might connect to spacetime emergence. Theoretical advances in quantum gravity and holography will attempt to bring de Sitter-like spacetimes into the same rigorous footing we have for anti-de Sitter models. Each advance will chip away at the space of plausible cosmic destinies. Meanwhile, thinking clearly about what time-stopping means helps avoid confusions. The naive picture of time as a river that can be turned off is misleading. The more precise statement is that if all macroscopic processes produce no net change, if there are no sustained gradients, no reliable clocks, and no lasting records, then the notion of experienced time evaporates. The parameter t in our equations continues to exist mathematically, and quantum fields still fluctuate, but there's no meaningful internal standard to say now is different from later. That distinction reframes the problem. Physics needs to tell us whether such a recordless, gradientless state is an unavoidable asymptote or one possibility among several, and whether processes that maintain memories and do work can be sustained or regenerated in principle. As you follow these threads from observations to theoretical proposals to thought experiments, a pattern appears. The questions that sound metaphysical at first glance are deeply scientific because they hinge on numbers and physical mechanisms. A measurement of W, a better determination of the top quark mass, or a detection or strong exclusion of primordial gravitational waves will alter the probability weights we assign to different cosmic endings. Meanwhile, theoretical progress on the quantum nature of horizons or on the mechanisms of spacetime emergence could radically reframe the terms of the debate. None of this is merely idle speculation. These are empirical and theoretical research programs with clear deliverables and stakes. It's also useful to keep a practical perspective. The timescales involved in the most extreme fates, black hole evaporation over 1067 years, or de Sitter recurrences on doubly exponential timescales, are so vast that they dwarf any conceivable civilizational planning horizon. That doesn't make the questions useless. They're a testing ground for our best physical theories, a place where conceptual assumptions are exposed and where new physics often gets born. Historically, big questions about the cosmos have driven technological and theoretical advances that pay off in unexpected ways. There are still active debates over precisely how to count entropy in cosmology, what microstates are relevant, and whether our universe's low-entropy past is a brute initial condition or a consequence of deeper dynamics. Those debates are the engine of progress. They motivate new observations, sharpen theoretical proposals, and invite cross-disciplinary insight. Whether the universe's eventual story is a slow, silent freeze, a violent rip, an abrupt vacuum change, or an endless chain of eons, the process of figuring it out forces us to refine our understanding of time, information, gravity, and the very nature of physical law. All of this sets up the next set of natural investigations, digging more deeply into the mechanisms that could reset entropy or that could make the initial low-entropy condition less mysterious. That means exploring bounce and cyclic models more carefully, investigating baby universe production in quantum gravity, sharpening quantum cosmology proposals like the no-boundary wave function, and seeking firm footing for holographic descriptions of de Sitter space. Each of those investigations brings both technical challenges and observational consequences. If any one of them produces a solid, testable prediction that matches observation, it could rewrite the way we think about beginnings and endings, and thereby rewrite the story of whether time, in any practical sense, ever truly stops. Picking up where we left off, a natural move is to look more closely at the concrete mechanisms. People have proposed to reset entropy, or to make a low-entropy beginning less mysterious. These ideas try to replace the brute fact, the universe started special, with a law or a process that does the setting for us. Some are conservative tweaks of known physics, others are bold rewrites of what space and time mean. Walking through them helps show what would be needed to avoid a long, quiet freeze, and what observations or theories could tip us toward one picture or another. Start with bouncing and cyclic models. The basic intuition is simple. Instead of one-off Big Bang that launches a single expansion forever, the cosmos might go through a series of phases, contracting, bouncing, and expanding again. If you can arrange a bounce that wipes out the accumulated entropy from the previous cycle, then every new expansion could start in a state that's effectively low entropy for the things that matter. That's attractive because it replaces an unexplained special initial state with a recurring process. But there's a catch that's worth stating plainly. Entropy tends to accumulate, and getting rid of it requires a physical mechanism. You can't just wave your hands and say reset. You need a way for entropy to be diluted, hidden, or converted into forms that don't spoil the next bounce. One way cyclic models try to do that is by using cosmic expansion itself as a diluter. Suppose the universe goes through a long period of accelerated expansion between cycles. That expansion spreads out entropy so thinly that, from the viewpoint of the next cycle, it's negligible. Penrose's conformal cyclic cosmology, CCC, uses a somewhat different trick. In the ultra-remote future of a given eon, his word for a cosmic epoch, black holes have evaporated and only massless radiation remains. Once only radiation survives, the geometry can be conformally rescaled so that enormously large and cold late-time configurations can be matched onto a new hot, small-scale beginning. The idea is mathematically clever. Conformal transformations change scales in a way that can turn an infinite future into a finite starting point. But it's controversial because it depends on assumptions about how mass and matter behave asymptotically. CCC is appealing because it offers an elegant mapping from an old, empty universe to a new, low-entropy beginning. But it requires both the right physics and the right observational signatures to be persuasive. Another take on cyclic behavior is ekpyrotic or ekpyrotic-inspired models, which come from ideas in string theory and brane cosmology. Instead of a violent, chaotic crunch, the ekpyrotic phase is a slow, highly ordered contraction that damps away anisotropies and inhomogeneities. When that contraction gives way to expansion, the universe can emerge very smooth and with the right kinds of small perturbations to seed structure. The virtue here is that the process itself, the slow contraction, removes the need for a special smooth patch at the outset. The downside is that one must explain what causes the bounce in the first place without producing catastrophic instability or leaving behind unmanageable entropy. All of these cyclic and bounce models are technically demanding. They push on the unknown regime of quantum gravity, because bounces need to navigate where classical general relativity would predict singularities. These bouncing ideas point to a general lesson. If you want to avoid a single, unexplained low entropy start, you need a physical way to erase, hide, or reassign entropy between cycles. That's a tall order, but not an impossible one in principle. It's exactly the kind of challenge that drives researchers into quantum gravity territory, where the usual rules of space and time might be different. A second family of ideas involves baby universes and cosmic reproduction. Here the idea is that parts of our universe could pinch off and spawn new, causally disconnected regions, that then inflate and begin new histories with fresh low-entropy initial conditions. The analogy people like to use is biological reproduction. A parent universe gives rise to offspring universes, and maybe those offspring can vary in their properties. The mechanism often invoked is quantum tunneling or some non-perturbative gravitational process. Under particular circumstances, a pocket of space can undergo inflation and become a new domain that from its own interior looks like a Big Bang. For inhabitants of the baby universe, the past is the inflationary patch. For observers in the parent universe, the baby is out of reach. From the point of view of avoiding heat death, this is interesting because it transforms a one-time event into an ongoing generative process. Universes can be born, each with its own arrow of time pointing away from its low-entropy start. It doesn't save the inhabitants of the parent universe from running out of usable energy, but it alters the global landscape by creating ever more fresh low-entropy pockets. The big uncertainty here is whether the physics actually allows such nucleation and what the rates would be. Making baby universes deliberately, say, by an extremely advanced civilization manipulating high-energy fields, is the stuff of science fiction at present. But theoretically, if such processes exist, they change the global accounting for entropy and observers. While bouncing universes and baby universe production try to explain special initial conditions dynamically, quantum cosmology seeks to give a rule for the initial state directly. The Hartle-Hawking no-boundary proposal and Vilenkin's tunneling proposal are prominent examples. The no-boundary idea pictures the universe's past as smoothly rounded off in Euclidean, time-rotated geometry rather than starting with a singular point. That mathematical trick yields a particular prescription for the wave function of the universe, and therefore for which initial geometries are favored. The tunneling proposal imagines the universe's birth as a quantum tunneling event from nothing into existence. Both are attempts to turn the past hypothesis into a calculable probability distribution rather than an unexplained postulate. They are elegant and have motivated lots of work, but they depend on how you define the path integral, which contours you choose, and how to interpret probabilities in a quantum cosmological setting. That's a conceptual minefield. Still, if a quantum cosmological proposal were sharpened and tied to empirical predictions about, say, the spectrum of primordial fluctuations, it would be a major advance. All of these dynamical and boundary condition approaches end up bumping against deep questions about what to count as entropy in gravity-dominated systems. That's where the holographic principle enters the conversation. Holography began with black holes. The insight that the maximal entropy inside a region is proportional not to its volume, but to the area of its boundary. This surprising observation, that information appears to live on surfaces rather than in volumes, has evolved into a broad hypothesis that spacetime itself may be emergent from lower dimensional degrees of freedom on boundaries. In some special settings, notably anti-de Sitter space, this idea is mathematically precise. The ADS/CFT correspondence gives a duality between a gravity theory in a bulk spacetime and a non-gravitational quantum field theory on its boundary. If something like that works for a cosmology with positive vacuum energy, de Sitter space, it would provide a way to count microstates and to make sense of horizon entropy microscopically. Why does that matter for whether the universe can freeze? If horizon entropy corresponds to a finite number of microstates, then a de Sitter universe has a finite information capacity, and over unimaginably long times you expect recurrences and rare fluctuations. That's the origin of the Boltzmann brain worry in a de Sitter setting. If instead, a deeper holographic theory shows that the effective state space is infinite, or that certain fluctuations are suppressed, the recurrence and Boltzmann brain issues could be avoided. The catch is that constructing a fully satisfactory holographic description of de Sitter space has proven tricky. Our best mathematical tools work best in negatively curved spaces. Positive curvature cosmology remains more of a frontier. Progress here would reshape our confidence about finite entropy conclusions. Let's dig into the Boltzmann brain problem a bit more, because it's a neat example of how a conceptual issue has practical implications for cosmological models. Suppose the universe approaches thermal equilibrium and then just sits there for fantastically long times. Even in equilibrium, random fluctuations can produce local pockets of low entropy for brief moments. Given enough time and the right degrees of freedom, a fluctuation could produce a brain with a fleeting pattern of neural activity that includes memories and perceptions of a coherent past. If such Boltzmann brains are much more common than brains produced by long, causal histories like ours, then statistical reasoning suggests most observers should be Boltzmann brains. That contradicts our observation that we live in a consistent, structured universe with correlated records and sustained histories. So how might a good cosmological theory avoid this paradox? One way is to make sure that ordinary observers outnumber Boltzmann brains overall. That can be achieved if the era in which ordinary observers arise is large compared to the tiny probabilities of fluctuations, or if the model avoids an eternal, stable thermal equilibrium altogether. A de Sitter future is particularly dangerous because it provides an eternal thermal bath and a finite entropy. If there's no terminator, some process that ends the eternal thermal phase, then Boltzmann fluctuations eventually dominate. Thus, from a Bayesian or anthropic standpoint, a cosmological model that predicts a de Sitter future may be disfavored unless it includes other features that suppress Boltzmann brains. That's why some cosmologists argue that a successful cosmology must either prevent eternal de Sitter equilibrium or provide a measure for counting observers that weights ordinary observers more heavily. This brings us to the measure problem in cosmology, which is about how to assign probabilities in situations with very large, possibly infinite ensembles. If inflation creates infinitely many pocket universes, or if time runs forever so there are infinitely many observers, then naive counts become meaningless. Different ways of slicing the infinite set, weighting by volume, by number of observers, by time, or by other criteria, give different answers. That ambiguity matters for big-picture conclusions like whether Boltzmann brains dominate. Resolving the measure problem is partly about mathematical consistency and partly about making our probabilistic statements physically meaningful. Progress is slow and often technical, but it's important. If we can't agree on how to count possibilities in an eternally evolving cosmos, then our statistical claims about what futures are likely are on shaky ground. Now let's think about the practical limits on life and computation in these late-time scenarios, because the imaginative question, could anyone do something to stop the freeze, is both interesting and instructive. Earlier we mentioned Freeman Dyson's idea of slowing subjective time to stretch finite resources into infinite subjective lifetimes. That's a clever trick if the background temperature continues to drop without bound, because you can operate at lower and lower energy scales and stretch the number of operations per unit available energy. But in a de Sitter universe with a fixed horizon temperature, you hit a hard lower limit on usable temperatures, and you can't cool arbitrarily far below that. Even without a cosmological constant, real engineering challenges, like extracting arbitrarily tiny amounts of energy from a very cold background or maintaining durable low-entropy reservoirs, impose limits. Black holes provide late-time fuel through Hawking evaporation, but harvesting that energy efficiently is a technical challenge and doesn't offer a path to indefinite processing if there's a hard background limit. A related question is whether information processing can be made arbitrarily efficient. Landor's principle gives a lower bound for the thermodynamic cost of erasing one bit of information. You must dissipate at least kT ln2 of heat into the environment, where T is the environment's temperature. That connects the cosmic environment directly to the cost of computation. If the environment has a non-zero minimal temperature, there's an irreducible cost to resetting memory, which gates the rate of reliable computation. Reversible computation can, in principle, reduce energy dissipation, but only at the cost of enormous complexity and strict control over noise, and it still eventually confronts physical limits like decoherence and error correction overheads. So whether a civilization can run forever is not just about raw energy, but about the thermodynamic cost of sustaining reliable information processing in a noisy, cooling, or horizon-limited cosmos. These physical constraints carry ethical and philosophical implications. If the long-term future of intelligence is finite or constrained, it reframes what long-term projects are reasonable. Should an advanced civilization devote resources to seeding new universes, if that's possible, instead of prolonging local activity? If baby universe creation is feasible, is there a moral argument to invest resources to create new low-entropy regions that might support life and value, even if one cannot reach those regions oneself? These are speculative questions, but they're the kind of practical philosophy that emerges when physical limits on persistence are taken seriously. The point isn't to give firm answers, but to show how physics informs questions about what long-term goals are even meaningful. Let's return to theory for a moment and ask, what would count as a decisive theoretical breakthrough that changes our view of the freeze? Two things stand out. First, a robust holographic description of de Sitter space would give a microscopic account of the horizon entropy and might show whether recurrences or Boltzmann brains are inevitable. If de Sitter has a finite-dimensional Hilbert space and the dynamics are essentially ergodic, then recurrences are unavoidable, and the freeze plus fluctuations picture becomes hard to avoid. If, on the other hand, the correct theory modifies these expectations, perhaps by giving an infinite-dimensional effective description or by coupling de Sitter regions to other sectors in a way that prevents equilibrium, then the long-term statistical arguments must be revised. Second, a confirmed detection that dark energy evolves in time, W not equal to -1, would alter the asymptotics. If dark energy decays or changes sign, the eventual fate could be very different from a de Sitter freeze. Those two kinds of breakthroughs, theoretical and observational, are the ones most likely to change the broad conclusions. Observationally, the near-term levers are clear. improve measurements of the dark energy equation of state, map the large-scale distribution of matter to learn how structure grows, refine constraints on primordial gravitational waves to understand the inflationary energy scale, and continue to pin down particle physics parameters that inform vacuum stability. On the astrophysical side, better catalogs of black holes and their masses, improved models of star formation shutdown and remnant production, and refined observations of the cosmic microwave background will all add pieces to the long-term puzzle. Some of the data we need is already being collected. Much more precise determinations will arrive over the next decades. Each incremental tightening of the observational picture narrows the space of plausible long-term scenarios. Meanwhile, tabletop and laboratory experiments continue to test the thermodynamic and information-theoretic building blocks of the story. Experiments probing quantum thermodynamics, demonstrating controlled Maxwell-Demon-type setups, and pushing the limits of reversible and low-energy computation teach us what is practically possible for information processing under thermodynamic constraints. Those lessons matter because the late time limits for life and computation scale from the microphysics. If we discover clever new ways to process information with less dissipation, that can extend the horizon for what advanced civilizations might achieve, even if it doesn't override cosmological constraints like the existence of horizons or a fixed background temperature. There are also conceptual moves that remain important. One is to refine what we mean by observer when applying anthropic or probabilistic arguments. The term observer can be slippery. Does it mean any physical system that briefly holds a configuration we might label as a brain? Does it mean a system with a sustained history, memory, and causal embedding? Different choices change the Boltzmann brain calculus dramatically. Another conceptual task is to sharpen our understanding of coarse graining, which degrees of freedom are physically relevant for macroscopic irreversibility in a gravity-dominated cosmos. Answering that helps pin down whether entropy really has a single sensible definition on cosmic scales or whether different contexts require different bookkeeping. There's also a practical methodological reflection here. Cosmology sits at the border between empirical measurement and deep conceptual work. Some of the hardest questions, the nature of the vacuum, the quantum description of horizons, the fundamental degrees of freedom behind space and time, are not easily decided by any single type of experiment. Progress usually comes from a mix, a theoretical insight that reshapes how to think about data, paired with a new measurement that discriminates between classes of theories. That interplay is what has driven cosmology forward for the last century, and it's what will drive progress on questions about heat death and the arrow of time. Before we wrap up, it's useful to translate these grand ideas into a few concrete thought experiments, because those often help clarify what's at stake. Imagine two hypothetical universes identical in all measured respects, except for one detail. In Universe A, dark energy is exactly a cosmological constant. In Universe B, dark energy is a slowly rolling field that will eventually decay and allow matter to redominate in the far future. In A, observers like us are likely to see a future that asymptotes to de Sitter space with finite horizon entropy and all the recurrence-type consequences that follow. In B, the long-term picture could allow new structure formation, renewed star formation, or different black hole fates, and it might avoid the Boltzmann brain problem entirely. Which universe seems more natural from our physical theories? Observations, particularly precise measurements of W and its time derivative, are how we would choose between them. This simple binary shows how a single measured parameter can have enormous implications for the distant future. Another useful thought experiment is to imagine an extremely advanced civilization trying to maximize the total number of conscious experiences it can produce. How should it allocate resources? To local survival, to building machines that harvest black hole evaporation late, or to endeavors that might nucleate baby universes? The optimal strategy depends on the physics, whether baby universes are possible, how expensive they are to produce, whether harvested Hawking radiation yields net usable work in a de Sitter background, and so on. The upshot is that questions about what an advanced civilization should do in the face of cosmological constraints are not purely philosophical. They're physics problems that depend on concrete facts about vacuum energy, horizons, and the thermodynamics of extreme spacetimes. All of the threads we've surveyed, bouncing models, baby universes, quantum cosmology, holography, Boltzmann brains, the measure problem, and the physics of information, are different facets of the central issue: how to understand the arrow of time, and what that understanding implies about the long-term prospects for change, life, and meaning in the universe. The broad picture that emerges is mixed. On one hand, the straightforward extrapolation of much of contemporary cosmology leads to a practical freezing of organized activity. A heat-dead, horizon-dominated, low free-energy future where macroscopic change is essentially impossible. On the other hand, there are plausible though speculative routes that would avoid that bleak endpoint. Evolving dark energy, cosmic bounces, baby universe production, or a quantum gravitational revision of horizon thermodynamics could all alter the asymptotic story. Which of these is true remains an empirical and theoretical question. The next decades of observational cosmology will narrow the space of options. Progress in quantum gravity and holography could change the conceptual landscape by clarifying what microstates count and what recurrences really mean. And experiments in quantum thermodynamics and information processing will refine what is practically possible for computation and life. Until those advances arrive, the most honest position is a probabilistic one. Some futures are more likely given current evidence, others remain plausible pending new data, and many fascinating conceptual puzzles remain to be solved. If there's a human moral in all of this, it's an epistemic one. Thinking about the end of time forces us to disentangle what physics can tell us robustly from what's speculative, and it sharpens the questions we actually have a chance of answering. The cosmic freeze is not just a gloomy science fiction image. It's a concrete hypothesis built from measurable parameters, thermodynamic reasoning, and mathematical models. That means we can do something about it intellectually. We can reduce uncertainty by measuring, modeling, and clarifying concepts. That's the good news. The more we learn about dark energy, quantum fields, and horizons, the clearer the long-term future becomes, and the better we can judge whether the daytime stops is a literal metaphysical end, an operational death of experienced time, or simply one among several eventualities the cosmos might realize.